Hello again. In this segment, we'd like to speak about the different kinds of forces that act on solids, because this is important in understanding how animals manage to hold their weights and the forces they're subjected to without failing or buckling in some way. Now, if you look at the structure of animals, you find that they can be idealized to two basic kinds of structures. Spheres, for example, my head is an idealized sphere, and columns, which might describe nicely my limbs and other parts of my body. My torso is also a kind of a column. Now, when we analyze how it is that bodies react to and respond to forces, then we have to understand something about the way in which those forces act on those basic, simple elements. Now, if you look at the different kinds of forces that are acting on our bodies, you find that they occur in several different ways. Probably the simplest is the kind of force that is known as compression. And compression is very easy to understand. I stole a fanoodle from my kids this morning, and so we're going to use this as a demonstration. In a compression force, we actually take forces and we apply them to both sides. So when I take my hand and I press it against here, I'm subjecting this fanoodle to a compression force. Now notice that as I subject it to that compression force, the length along the fanoodle shortens. Now, ordinarily, you also see an expansion of it. It's hard to see that in this case because this is a special kind of bubbly material, but you can see very easily how it is a compression force actually makes this shorter in this direction. Another force that's actually opposite to compression is tension. And tension is just the opposite of compression. Here I'm going to take a fanoodle again. Let's zoom out a little bit here. And I grab both sides and I pull. And when I pull, it lengthens. You can see maybe that if I pull on this, that the distance between those marks increases. And that is a tension force. The other kind of force that we want to be paying attention to is a force called torsion. And in the case of torsion, what we do is we twist one end in the opposite direction we twist the other. So if I take the fanoodle and I twist it, that's a torsion force. And you can see the ridges along the surface of that start forming into a helix that wraps around the fanoodle. Now, one of the reasons why this is important to understand is that certain kinds of biological materials, and this is true for any kind of material, they are sometimes very weak in compression and strong in tension, or vice versa. Might be weak in tension or strong in compression. For example, concrete is a material that is very strong in compression, but is very weak in tension. If you have a concrete pillar and you try to pull it apart, you'll find it's actually quite easy to do that. But biological materials are, in many ways, just the opposite. And they can be engineered in various ways, which we'll be speaking about, where they can be made simultaneously strong in tension and compression, or relatively strong in tension and weak in compression. And understanding how the different forces act on that, the mix of compression, tension, torsion forces, and those kinds of things, are important to understanding how it is that animals not only can hold themselves together, but also manage to hold themselves together in a safe way, that is, without failure. Now, there is one more kind of force that we need to talk about, because this will be very important in understanding how it is that bones work. And this is a mechanism of failure called Euler buckling. And Euler buckling is very easy to demonstrate. If you take a column of any sort, you can put a weight on it. You can put a weight on it and the column will manage to support that weight. Now, if you put too much weight on a column, you'll get what's called a buckling failure. That is, it will go this way. And this is not capable of supporting the weight anymore. In fact, it will go right down. So this is a unique mode of failure that bones, actually, and many other kinds of column-like biological structures are subject to. This Euler buckling is key to understanding not only things like how bones scale in size with body size of the animals, how trees hold themselves up, and a whole host of other kinds of phenomena. Okay, well that's all for now, and we will see you in another segment. Thank you for listening.